Hey everyone. In this video, I'm going to go over the ATC Worksheet 1 for Chem 118C. So first, I'm going to go over the general concept review before going over the practice problems. So first, let's go over the oxidation of aromatic compounds containing a benzylic hydrogen. So whenever we react a benzene with R groups and the first step as KMNO4, H2O, and heat, with a acid workup step following up, then we have to look for at least one benzylic hydrogen to oxidize the R group into a carboxylic acid. So for example, for the first example problem, we see that this R group has two benzylic hydrogens, which accounts for the at least one benzylic hydrogen. We see that we are reacting it with KMNO4, water, heat, and an acid workup. So we're going to convert this R group into the carboxylic acid. So in the next example problem, we see that this carbon here does not have any benzylic hydrogens, which means that it will remain unreacted. Whereas this carbon here has three benzylic hydrogens, which accounts for the at least one benzylic hydrogen to oxidize all the way down to a carboxylic acid. So for the next problem here, we see that this benzene has two R groups where these two R groups has one benzylic hydrogen reacting with a KMNO4, water, heat, and acid workup, converting those two R groups into the carboxylic acid. Then let's go over the oxidation of alcohols. So whenever you see CrO4, H2SO4, and water, think of Jones reagent. And Jones reagent is a stronger oxidizing agent than PCC. So there's going to be three different alcohols that you can start off with. You can start off with a primary alcohol, secondary alcohol, or tertiary alcohol. So let's start with our primary alcohol first, where this alcohol is bonded to a primary carbon because this carbon is only attached to one other carbon. If you react this primary alcohol with Jones reagent, which is the stronger oxidizing agent, you are going to fully oxidize this primary alcohol down to a carboxylic acid. And oxidation is basically adding oxygen bonds to the group, while reduction is removing oxygen bonds to the group. Another way to think about it is that oxidation is removing hydrogen bonds, whereas reduction is adding hydrogen bonds. So let's say you reacted it with PCC instead, which is the weaker oxidizing agent than Jones. You are only going to oxidize this primary alcohol into an aldehyde. And PCC is a weaker oxidizing agent than Jones because we see here in the aldehyde, this carbon only has two bonds to oxygen, whereas the carboxylic acid product here from Jones has three bonds to oxygen. 1, 2, 3. Now let's move on to the secondary alcohol. If you react this secondary alcohol, which is bonded to a carbon that's bonded to two other carbons with either Jones or PCC, it wouldn't matter, then you are going to get a ketone. Now let's move on to the tertiary alcohol. If you react a tertiary alcohol with Jones or PCC, you are going to get no reaction because the carbon that's attached to the alcohol does not have a hydrogen to remove or add extra oxygen bonds to. So in these reactions, the most complicated case would be the primary alcohol because it would matter if you choose either the Jones reagent, the strong oxidizing agent, or PCC, the weaker oxidizing agent. So now let's move on to the conjugate addition reactions. So let's say we have an enone here, which is an alkene, which is the ene, and then ketone, which is the one. Alkene right next to a ketone. And you are given either a soft nucleophile or a hard nucleophile. So let's draw out the resonance form of the enone here, which I have done here. We see that in the resonance form, we see that this carbon here has a positive formal charge, whereas this carbon here from the carbonyl carbon does not have a positive charge. So that means that in the enone, this carbon here has a larger partial positive charge than the carbonyl carbon because of the resonance structure. We see in the resonance structure that this carbon has a full positive formal charge, where soft nucleophiles like nitriles, enolates, cuprate ions can attack this soft nucleophile with the bigger partial positive charge. But if you are given a hard nucleophile like LiALH4, Grignard, RMGBr, or RLI, then you are going to attack the carbonyl carbon with the smaller partial positive charge. So as an example, we're given this enone here, a nitrile as the first step, second step as acid workup. So since we're given a nitrile, which is a soft nucleophile, we can only attack the carbon with the bigger partial positive charge, which is this. So when that happens, this double bond is going to move up here, kick up this carbonyl bond up onto that oxygen. Then we have this intermediate where this second step of HCl will protonate the negatively charged oxygen here. Now we have an enol here, where this enol will tautomerize into the carbonyl stable form. Now let's go over the synthesis of nitriles via SN2. So let's say we had a primary substrate with a good leaving group like bromine and NaCN or KCN, which is a weak base strong nucleophile. This will indicate an SN2 reaction where this nitrile will attack the substrate and kick off the bromine leaving group, forming our nitrile. Now let's go over the hydrolysis of nitriles. So whenever you have a nitrile and you add acids such as H3O plus or H2SO4 or H3PO4, then you're going to hydrolyze this nitrile into a carboxylic acid. So this red labeled carbon is this red labeled carbon here of the carboxylic acid. And for the mechanism of this hydrolysis of nitrile, two important things to keep in mind are you would protonate the group that you want to leave to turn it into a good leaving group, or you would deprotonate the group that you want to stay, making it into a bad leaving group. So both of these points are going to be a pattern throughout Chem 118C or throughout the future chapters. So in the first step of the mechanism, this nitrile here will get protonated by the acid that we added, in this case H3O plus. Then after that, we have activated this carbon that's triple bonded to the nitrogen. It became more electrophilic. Then this water here came from this H3O plus. It will attack that carbon, kick this triple bond onto the nitrogen, one of the bonds into the nitrogen, giving us this intermediate right here. Then this water here that attacked is now this water. And now the nitrogen has a neutral charge. So in our end result, we want a carboxylic acid, which means that we want to deprotonate the group with the oxygen. So we're going to deprotonate this group with the oxygen with a water. And we want to get rid of the nitrogen because we see in our carboxylic acid that we want to get rid of the nitrogens. So we're going to protonate that group. So we're going to protonate this nitrogen with another H3O plus. And after we have done that, we activated this carbon that's double bonded to the nitrogen, making it more electrophilic, where another water molecule can come and attack that carbon, kick that double bond up onto that nitrogen, where this water molecule that attacked is now this water molecule. And we see that in our carboxylic acid, we want to keep our oxygen groups. So we're going to deprotonate this group to make it stay, giving us this intermediate. And we want to get rid of this nitrogen group. So we're going to protonate that group to make it into a good leaving group. So once we've protonated this nitrogen, we're going to reform our carbonyl and kick out the good leaving group that we just formed by protonating the nitrogen group here. And after we reform the carbonyl here, our very last step is to use the most basic species we have in the solution, which is the NH3, to deprotonate that positively charged oxygen, giving us our carboxylic acid here. So these 2 points are a big theme for these mechanisms. Now let's go over the practice problems related to the concepts that we just went over. So we see that we have KMNO4, H2O, heat, and the acid workup as a second step. So that means that we have to look for our benzylic hydrogens. We see here this carbon does not have a benzylic hydrogen, so that will remain unreacted. This R group has 2 benzylic hydrogens, which will oxidize down into the carboxylic acid. Okay. And now we see CrO3, H2SO4, and H2O, which we said earlier that is Jones, which is a strong oxidizing agent. And we have a primary alcohol. So since we have a primary alcohol, we're going to oxidize that primary alcohol down all the way to the carboxylic acid. where this carbon here, this carbon here. Okay. So now we have an enone here, which is an alkene right next to an ketone. We have a soft nucleophile, which is the Cn minus. And we said earlier that the soft nucleophile will attack the more partially positive carbon. And after the keto-eno tautomerization step, we're going to get this structure here, intermediate here. So this is after the first step. And for the second step, we add acid. So we have a nitrile here and acid. That this is going to be hydrolysis of nitrile into carboxylic acid. So after the second step, we're going to hydrolyze this nitrile into a carboxylic acid. Okay, so this carbon here of the nitrile is this carbon here of the carboxylic acid. Okay, and now we see that we have a primary substrate, a good leaving group, chlorine, and a weak base, strong nucleophile, nitrile. So this would indicate an SN2 reaction where the nitrile will attack that substrate, kick out the good leaving group, and give us this nitrile as the first step. And then we see here in the second step, we added acid and heat, which would hydrolyze this nitrile into a carboxylic acid. So this pink carbon here of the nitrile is this pink carbon here of the carboxylic acid. And for the mechanism of this 1D is that the first step is to do SN2, where the nitrile attacks that substrate, kicks off the good leaving group, forming a nitrile here. And then we bring in our second step of the acid workup here, where this nitrogen will get protonated. And after this nitrogen gets protonated, we're going to activate this carbon, which becomes more partially positive. Then the water that we formed will be able to attack this carbon, kick up one of the bonds of the triple bond onto the nitrogen, which makes it neutral. And now we do the whole theme of protonate the group that we want to leave and deprotonate the group that we want to stay. So since we want to keep a carboxylic acid, we want to keep the group with the oxygen and get rid of the group with the nitrogen. So we see here that this OH2 plus group we want to keep. So we're going to deprotonate them with the water. We want to get rid of this nitrogen group. So we're going to deprotonate that group with the acid. And after we protonated that nitrogen, this carbon double bonded to the nitrogen is more susceptible to a nucleophilic attack. So this water here is now able to attack this carbon, kick up one of the double bonds onto that nitrogen. And then now we do that whole thing again. We deprotonate the group we want to stay, protonate the group we want to leave, reform our carbonyl, kick off the good leaving group that we just formed. And then a very last step here is to deprotonate the positively charged oxygen with the NH3 group that just left, giving us our carboxylic acid here. So I would practice these mechanisms over and over again, but not only to memorize it, but understand the reasoning behind each arrow. So you will be able to get it during exams. Okay, so now let's go over synthesis of this worksheet problem right here. So we see here that we start off with a cyclopentane with a ketone, bromine, and we have the same thing. So the only thing that changed we see here is the bromine with carboxylic acid. So we see that we could form a carboxylic acid. We could form a carboxylic acid through the hydrolysis of nitrile. So we could say that this bromine got converted to a nitrile, like this, and then we just hydrolyze that nitrile into the carboxylic acid. But if you try to do the first step as NaCN, then this Cn minus will not do SN2 here. And that's because there's another electrophile that is competing with that electrophile. So what would happen instead is that this nitrile will attack that carbonyl carbon and kick up that carbonyl oxygen up there. Then we'll get this and this, which is not what we want. So what we would have to do is we would have to protect the ketone, the carbonyl, and avoid that reaction. So we have to use a protecting group like an acetal to form the acetal protecting group. So the first step here would be to use this protecting group. And after the first step of that, we are going to protect the ketone, giving us this here. Now the carbon connected to the bromine is the electrophile that can react with the nitrile. So we're going to do the second step as NaCN and acid H2SO4, which will do SN2 and substitute that bromine with the nitrile. Okay, and then the very last step is to add acid and heat, which does two things. It will hydrolyze this nitrile into the carboxylic acid, and it will deprotect this acetal and convert it back to the ketone. Okay, so that's one of the synthesis routes. There's another route that you could do here. So let me redraw this reactant. Bromine, and we see here ketone and then carboxylic acid. We see that we added an extra carbon, which is this carbon here. So what you could have thought of was a Grignard reagent. So it could be like this Br here got converted to the MgBr, and the electrophile that we would add to make this Grignard work would be CO2. But we would have to protect this ketone as well, because once we form this MgBr, then this carbon here that's connected to the Mg can do an intermolecular reaction and we attack that electrophilic carbon. So we would have to protect that group as well, that ketone group as well. So the first step is to protect the ketone. Okay, and then after the first step, we get this acetal, Br, and then to form our Grignard, we just add Mg, which creates our MgBr here. So second step, Mg, and then we could add ether as a solvent, ether, and then now we have our nucleophilic carbon attached to the MgBr, which we can add CO2, giving us this. And then the very last step here is to add acid, which would do two things. So one of the things that it will do is that it will protonate this carboxylate into the carboxylic acid, and it will deprotect this acetal and convert it back into the ketone. So here are the two routes that you could go to make the synthesis work. Okay, so let's go for the next synthesis. We see that we started with the cyclohexene and we opened up the ring here. So then what I think of when I see alkenes in the ring that opened up with carbonyls is I think of the ozonolysis reaction. So the first step would be O3, which is the ozonolysis. And what that does is that you think of scissors and you snip the alkene in half and then add a carbonyl right there. So after the first step of ozonolysis, you would get this open chain here. And we see here that this carbon had a hydrogen. And now we could redraw this to make it look nicer. We see that we have 1, 2, 3, 4, 5, 6, 7 carbons. So we're going to draw 7 carbons, 2, 3, 4, 5, 6, 7, where carbon 2 had a carbonyl. Carbon 5, 1, 2, 3, 4, 5 had a methyl. And then carbon 7 had that carbonyl. So let's make sure 1, 2, 3, 4, 5, 6, 7. And for the ozonolysis, there's 2 steps. The first step is the O3. The second step would be the ether looking like structure, which is the sulfur thing. So the first step is O3. Second step is the SCH3 2. And it's most likely that you don't need to know the mechanism for the ozonolysis, but more important to know what product comes from reacting an alkene with ozonolysis, which snips this alkene in half and makes a carbonyl in between that. So then we see here that our very last step here, that what we need to do is to oxidize this aldehyde into the carboxylic acid using an oxidizing agent, strong oxidizing agent, Jones, which will strongly oxidize this aldehyde into the carboxylic acid. So the third step here would be Jones. Okay, so we are done with the synthesis problems. Now we're going to rank the following from the most to least acidic. Most acidic would be A, the least acidic would be I. Okay, so to determine the most and least acidic compounds, what I like to do is I like to deprotonate the acids and determine the stability of the conjugate bases. If the conjugate base is more stable, then that means that you are coming from a more acidic compound. But if the conjugate base is less stable, then the acid is weaker. And what determines the stability of conjugate base is the ability to do resonance and have inductive effect. So the more delocalized the negative charge is in the conjugate base, the more stable you are, and therefore the more acidic acid you came from. So these are the compounds conjugate bases where I deprotonated every single hydrogen here. And we see that in this case, this negative charge on the oxygen can do resonance both ways, 1, 2, which gives it a pKa of -9. So the lower pKa that you have, the more acidic you are. Okay. And then we see here, this compound A has the most resonance out of every single one, because this negative oxygen can resonate both in 2 ways. So the next most acidic compound would be this with the pKa of 0.2, because this carboxylate negative charge can do resonance, and it has inductive effect of the most electronegative atom, fluorine, and 3 of them. So the inductive effect is pulling the negative charge away, making it more delocalized. And since it's more delocalized, it will become a more stable conjugate base. And if you're a more stable conjugate base, you came from a more acidic hydrogen. Then our next most acidic would be this compound with a pKa of 0.64. It's similar to the B compound, but the only difference is the chlorine. Since chlorine is less electronegative than fluorine, chlorine will have less inductive effect than fluorine does. Then we will have D. The only difference is that we're missing 1 chlorine compared to C. And then for E, these chlorine atoms are farther away, reducing the inductive effect. And then we see that the pKa of E and F are 3 to 5, which are really similar. So they are similar in acidity. And then for G, we see that this nitrogen here is less electronegative than oxygen, which means that it is not as capable of holding that negative charge that oxygen is, which is why the pKa is higher, making it less acidic. And the pKa could be 15 to 16 or 22, depending on what kind of professor you have. So G and H could be replaced depending on what kind of professor you have. And we see here the similar reasoning. This carbon has a negative charge rather than oxygen, which makes it less likely to hold that negative charge since carbon is less electronegative, making it not as acidic as the oxygen negative charge is. Then our highest pKa, the least acidic, would be this negative charge carbon, because we see that this nitrogen here is donating electrons, making those electrons very close together due to inductive effect. And since those electrons are very close to each other, they would repel and become very unstable conjugate base. And since it's a very unstable conjugate base, then it is not a very good acid, making it the least acidic compound. Okay. Then let's go rank the following from the most acidic to least acidic hydrogen here. We see that we have benzoic acid, which is a benzene connected to a carboxylic acid, and we have different groups here. It could either be electron donating group or electron withdrawing group. So let's go over that concept of electron donating group and electron withdrawing groups on the acidity of benzoic acid. So let's go over some terms here. If we have a group, the ortho position of that group is 1 carbon away. The meta position of that group is 2 carbons away. And the para position of that group is 3 carbons away. So if you add an electron donating group to benzoic acid, it would decrease the acidity because it would donate electrons into the system, which makes the system not as delocalized, making it less stable. So let's say we added an electron donating group like NH2, and here are the resonance structures of NH2. We see that in the resonance structures, we have a negative formal charge in the ortho positions and the para positions. So we see here an electron donating group like OCH3, the ortho and para positions of that OCH3 is partially negative, which makes that system negatively charged. Whereas the electron withdrawing group like NO2, the resonance structures of that structure gives a positive formal charge on the ortho and para positions, making the system more partially positive and able to support the negative charge on the conjugate base more. So we see that in the conjugate base carboxylate, the electron donating group will not support the negative charge because those negative charges will repel each other, making it less stable, which is why electron donating groups will reduce the acidity, whereas the electron withdrawing group will provide a positive charge to the system, supporting the negative charge more and enhancing the acidity. So let's go over the practice problem of that now. So we see here, this NH2 is an electron donating group. The CH3 is an electron donating group, which is an R group, but it's electron donating through the inductive effect, not the resonance effect. Whereas the NH2, it has a lone pair of electrons that I could resonate and donate through resonance to, donating electrons through resonance. We see here, this is an electron withdrawing group, NO2. This has no group, and this has an electron withdrawing group here. So the most acidic one would have an electron withdrawing group that is ortho or para to the carboxylic acid. We see here that this NO2 is para to the carboxylic acid, making it the most acidic compound because this NO2 gives a partial positive charge to the ortho and para position, which is close to this carboxylic acid. And if this carboxylic acid gets deprotonated, giving its oxygen a negative charge, this negative charge is able to be supported by this partial positive charge. Whereas this is our second most acidic hydrogen, carboxylic acid, because the electron withdrawing group here only provides a partial positive charge on the ortho or para position, which is not directly under the carboxylic acid. It's still a positively charged system, still supporting the carboxylate, but not as strongly as the first one here. Then we'll have the neutral one with no group, and then the next most acidic would be the one that would donate the least electrons. So since this R group is donating via inductive effects, not giving a full negative charge, then this compound here would be more acidic than the compound that is actually giving a negative charge to the system. So we see here, this negative charge on the carboxylic acid is going to repel the conjugate-based negative charge here, making that very unstable and making it not very acidic. So this electron donating group here is able to donate through resonance, whereas this R group is not able to donate through resonance, which is why there's not as much of a negative charge. It's smaller, making it not as unstable as this over here. So here are the rankings, A to E, from which is the most acidic hydrogen.